Okay. So now I want to end by going back to that flow chart that I gave you, which sort of set up the learning problem. And now we have discussed a little bit and we have understood the conditions where learning is feasible, and that's added some constraints and some other ingredients into that learning problem setup. So let me bring that flow chart back, add the things that we need to add to get our final learning problem setup, within which we now know that learning is feasible through this two-step process for at least finite hypothesis sets. So speed erase. Okay, so let's summarize the learning setup with this two-step learning process in mind and see what's new. What do we have to add? So the two-step learning. Okay, so this is very important. So in the two-step process, the first step is you have to establish that E out of G, so learning produces G, E out of G is approximately equal to E in of G. And step two, you have to ensure that or you have to arrange it such that E in of G is approximately equal to 0. So this means you have to appropriately choose your hypothesis set. Okay, so let's box that. So this is new. This is the two-step learning. Now let's look at our flowchart. Remember, the flowchart starts with the target function. So it starts with the target function. Okay, and then you have the data. Okay, and then you have the algorithm, which uses the data. Okay, and the fixed hypothesis set is also feeding into the algorithm, and the algorithm produces my final hypothesis G. Okay, so this basic, the final hypothesis G that should approximate F, and this basic structure remains. Okay, now we understand the need for the hypothesis set to be fixed ahead of time so that we can make some claims, because about E out versus E in, we can link E out to E in, and this has to be done theoretically, and it's essential that the hypothesis set is fixed. You have your fixed hypothesis set H. The data is not going to change. Okay, so the data is the data. Okay, so the data set is x1, y1, x2, y2, x n, yn. Okay. Now, how did we get the data set? Okay, and we get the data set invoking the target function on data points x1 up to xn that are generated by some random process. That's new. Before we didn't talk about how we got the data set. Now we can tell the client that you need to give me IID data generated according to whatever the distribution is that generates data. So there's a distribution, we'll call it P of x. Okay, and this distribution is generating the data IID, independent, identically distributed data, x1, x2, up to xn. Okay, and now the target function, you have to arrange it so that you can indirectly apply the target function to these data points to get y1 to yn. And before we had the target function as being a deterministic target function, f of x, but now we see that the theory can accommodate the most general type of target function, a target distribution. So target distribution. Which what we used to call f as a deterministic function, but it can, all the theory flows if it's a distribution p of y given x. Now we will still mostly stick with f, but I'm just mentioning here that, it's general, the theory flows, nothing is affected if the target function becomes non-deterministic. It's a target process, it's a random process that generates the y given the x. Okay, and so, the target function f generates the data. The y values in the data generate y values. Okay. There's one more important role that the input distribution P of x plays. The random process that's generating data points. It generates your data IID, and it also generates the test point, the independent test point. Okay, so it also generates the independent test point with respect to which we compute E out. Okay, and that corresponds to the statement that, you know, when you're testing me, when you're thinking about Eout and how you quantify whether G is equal to F or approximately equal to F, you must test me on when you're trying to approximate, make this claim that the step 1 of the learning process has occurred. It must be the case that Eout refers to the same bin that got you your sample. And what that means is that the input distribution that generates your data in your data set must generate a test point. Important. The bins must match. Okay, and that would more or less be it. We wouldn't really have to add anything more, except now we see that, you know, depending on the user and the application and the problem, you know, you may want to specify the error measure. Okay, so there's now also the error measure. Okay, and the error measure actually serves 2 roles. The first role it serves is to grade the hypothesis in sample. So you use the error measure, whether it's a risk matrix or a different kind of error measure. You use the error measure to grade the different hypotheses in your hypothesis set, and that's the criterion by which the algorithm is going to decide which hypotheses look good and which do not. Okay, so it's going to affect the algorithm, and typically the algorithm is going to pick the final hypothesis G that looks best with respect to this error measure. And then when you're comparing G to F on this random test point, you must also use the same error measure. Okay? So this E in approximately equal to E out applies providing you're using the same error measure to make, evaluate both. So the error measure affects the algorithm in terms of how you compute E in of G, in terms of how you grade the hypothesis that leads to the picking of G, but also in terms of how you compute E out. Okay? And that's the full learning setup there with all its bells and whistles. So let's call this the learning setup. Okay. And there are 2 important ingredients. One is sort of the flow chart of what's going on, and this establishes how you generate the data and perform the learning, and also establishes the 2 criteria that we need to accomplish in order to ensure us that learning has occurred. So the learning setup. And this together is the setup within which we can say learning is feasible. It's feasible, okay, providing you have fixed your hypothesis set and, you know, ensured that you can accomplish step 1. Okay, and then we see whether step 2 is accomplished by performing the picking of G and seeing whether its E in is low, and if not, important, it's possible to fail. So learning is feasible only when it's also possible to fail. Only when it is also possible to fail. Okay, and so there you have a nice 1-slide summary of the entire learning setup and the discussion up to now. Signing off, till next time.